Okay, section 6.1 is a continuation from last time, and instead of relative extrema, we're going to talk about absolute extrema, and this is page 67, or starting on page 67 of your course notes. So absolute extrema. The absolute min or max is the largest or smallest of all the values in the range of the function. So last time we talked about relative max or min, which was a maximum within a certain area, but this would be overall. And of course, we want to talk about a specific interval. It could be negative infinity to infinity, depending on the graph. But we were talking about within a relative area, within an interval. So in the first image here, we have a absolute maximum at the top of this parabola. Okay, at the very top point, there is no point higher than that. Now, we don't have an absolute minimum because both ends are going to negative infinity. So there is no absolute minimum. The right graph, there's no absolute min or max because there's no, they go on forever in both directions. So I should go back to this first one. There is an absolute maximum at x equals c. Right here, this point is labeled with a x value of c. Okay, so the extreme value theorem states that a continuous function on a closed interval, closed, remember both ends are closed circles, not open, will have both an absolute max and an absolute min somewhere in the interval. The critical point theorem goes a step further. It says if f is continuous on an interval, and f has exactly one critical number at x equals c, thus, if f of c is a relative max or min, then f of c is absolute. Okay, so there is exactly one critical number in an interval, then if it's a relative max or min, then it's the absolute maximum because it's the only one. So some examples. Find the locations of any absolute extrema for the following graphs. Part A, look at the regions. So we have x1, x2, and x3 on graph of part A. So here's x, these are the x values. Okay, now it doesn't give us a interval, so that means we're going from negative infinity to infinity. Okay, so looking at this, these arrows are going down forever, so we have no minimum. Okay, they're going down to negative infinity. However, the tallest value you can see is at x equals x to the third x sub 3. Okay, so that's the tallest or the highest point. So that would be the absolute max, absolute extrema, the absolute max. In part B, you can see we have neither. The graph is going up positive infinity and down to negative infinity, so there is no absolute extrema. A couple more examples on the next page of your notes, page 68. Looking at part C, these are both going up to positive infinity, so there's no maximum, no absolute maximum. However, we do have an absolute minimum here where we're not going any lower than this lowest point of the parabola. So we would have a minimum at x equals x sub 1, whatever x value that is. For part D, we don't have we do have a maximum, right? Because this point here, we have no arrows going to infinity. So this is a closed interval. Notice again that word coming back. So both endpoints are shaded in. So we have a max at x sub 1, okay, at this x value. And it looks like our minimum value is right here. So that would be x equals x sub 2. Okay, now we have a few examples where we are not given a graph but an equation. Find any absolute extrema as well as the values of x where they occur. Okay, so we're going to want to use our past known learning, what we've learned in the past about these, to find our solutions. Okay, so for part A, we want to find critical numbers. Okay, now remember to do that, we first want to list our domain, which in this case we don't have any domain restrictions, so we don't have to worry about that. So we set the derivative equal to 0. So that would be 3x squared minus 12x plus 9 equals 0. We can divide all of this by 3 to make our factoring a little bit easier. So factoring it, we get x minus 3 times x minus 1 equals 0. So x equals 1 or 3. Okay, so now all we have to do, we're really just looking again for the absolute minimum and the absolute maximum. Okay, so let's make a little chart. Let's have our x and our f of x values. Okay, now remember we're plugging it into the original function to find the f of x, not the derivative. Okay, now the other thing we want to know is that we found two critical numbers, 1 and 3, but we also need to check the endpoints given. So we're going to check 0, our critical numbers, and then the max x value, 5. So we're going to plug each of these in to our function. Now for the sake of time, you can pause the video and double check these, plug them in, but you should get these values. Okay, so we have an absolute max at x equals 5, and we have two absolute minimum values because they are the same. Okay, so again, you want to check the endpoints as well as your critical numbers. All right, our endpoints were 0 and 3. We have f of x equals x squared minus 4 all to the 1/3 power on the interval -2 and 3. Our endpoints are -2, which is already a critical number. Next example, part B. Part B, in your notes, we have f of x equals 1 minus x divided by 3 plus x over the interval 0, 3. Okay, so we want to first find our derivative. So our derivative would be the denominator times derivative of the numerator, which would be a -1, minus the numerator times derivative of the denominator, which is just 1, so I'm not going to write it, divided by the denominator squared. So if we simplify that, we get a -3 minus x, because we're distributing this -1 to each term, and then -1 plus x over 3 plus x quantity squared. So we end up with a -4 over 3 plus x quantity squared. So that's our derivative. So you can tell if we set the derivative equal to 0 to find our critical points, there is going to be no values. Okay, there's no solution to that equation. There's nothing we could plug in for x that will get us 0. Because if we plug in a -3, we'd have 0 in the denominator, which would mean it's undefined. Okay, so what we're going to do then is just check the endpoint. So part B, so we will just check those in a chart real quick. We have 0 and 3. Again, we're plugging them into the original equation. If we plug in 0, we will get 1/3. You can try it. And if we plug in 3, we will get -1/3. Since these are the only numbers we're checking, there's no critical numbers in this interval, in this closed interval, then that means x equals 0 of 1/3 is the absolute max, and -1/3 is the absolute minimum. Okay, last example, part C in your notes. So we want to find the derivative of this. So we first take the derivative of the outside function. So we multiply 1/3 out front. And then we decrease our exponent by 1. So we have -2/3. 1/3 minus 1 is -2/3. Then multiply by the derivative of what's inside the function. So the derivative of x squared is just 2x. So if we simplify that a little bit, we get 2/3 x, right? We're multiplying these out front. X squared minus 4 to the negative 2/3. So to find our critical numbers, we want to set this equal to 0. Okay. So if we factor x squared minus 4 to set each of these factors equal to 0, we get x plus 2, x minus 2, and of course all of that is to the negative 2/3 power. Okay, we set each of these equal to 0, and we get x equals 0, negative 2, and 2. How 3? So when we check our points, we will check all of our critical numbers. We should probably go in order, huh? Negative 2, 0, 2, and 3. So all of our 3 of our critical numbers and our endpoints. If we plug in negative 2 to the original function, not the derivative, we get 0. If we plug in 0, we get negative 1.59 approximately. And if we plug in 2, we get 0. And if we plug in 3, we get approximately 1.71. So that means, these are all of our critical numbers. So that means x equals 0 at negative 1.59 is our absolute min. And x equals 3, y value of 1.71 is our absolute max.